Hello guys, welcome to H2O, the A to Z of chemistry. I'm Dr. Ritu Johar, your educator for this course on general organic chemistry, and I hope you are enjoying this course with me. So today we will be beginning with GOC part 2 lecture number 6, but make sure you watch the previous ones before viewing this one. In GOC part 1 we've had a detailed discussion on nomenclature of organic compounds, and now in GOC part 2 we are having a detailed discussion on isomerism in organic chemistry. Till now, in the first 5 lectures, we've had a detailed discussion on the structural isomerism, and now moving further, we will be starting with the discussion on stereo-isomerism. Now, this is a very important topic, and in fact, trust me, the students, they do find a difficulty in understanding the concept. But with us, I am assuring you that you will be able to understand the concept very well. Why? I'll tell you that. Well, stereo-isomerism is going to be an isomerism. So it is going to be that compounds, they will be having the same molecular formula. In stereo-isomerism, the compounds, they also have the same structural formula. This means that how the atoms, they are linked to one another, that is also going to be the same. So what is the difference? Well, the difference is in the spatial arrangement of the atoms in the molecule. If that is different, the isomerism that we will be having will be called as stereo-isomerism. And for this, what we are going to do is that I have made some clay models for you people. So I will be showing you that, and I will be explaining you the isomerism with those models. So it is going to be easy for you to understand looking at those models. If I draw the diagrams, I will be doing that also. We will be having the proper diagrams also for all the structures that I will be showing you, so that you can draw them in your notes that you also have to do. But I will be showing you all the models. They will be not very nice models. I've tried my level best to make them, but they may not be at proper angles and all, but I will be able to explain you the concept with those, because it is the spatial arrangement of atoms. So why not see them actually and then understand? So that is going to be the difference in this lecture. You are going to understand the whole concept with the help of some clay models, right? And now we will be having a brief introduction of what is stereo-isomerism, and then we will be discussing one of its type, geometrical isomerism, in detail, where we will be talking about Cis-Trans isomerism, then Syn-Anti isomerism, and then EZ isomerism. So I hope you are all excited to look at some clay models and understand the concept. So let us begin. Let us begin the discussion by going back to the table where we had first of all classified isomerism. So isomerism, you all know that this is a phenomenon where we will be having two or more than two compounds which will be having the same molecular formula. There will be a difference in their properties. It may be physical properties, it may be chemical properties, it may be both of them, but the molecular formula for the compounds, that is going to be the same. And then we have two types of isomerism. One is structural isomerism and the other is stereo-isomerism. So structural isomerism is what we have already discussed, the 6 types of structural isomerism: the chain isomerism, position isomerism, functional isomerism, metamerism, ring chain isomerism, and tautomerism, which we winded up with the discussion in the last lecture. And now we will be starting with the discussion on stereo-isomerism. And in stereo-isomerism, it is further of two types: configurational isomerism and conformational isomerism. Configurational is going to be further of two types, geometrical and optical. And it is this geometrical isomerism that we are going to discuss today in detail. And then we have conformational isomerism, where we will be having rotational isomerism and amine inversion. And this is going to take quite some time, where when we will be reaching this. Alright. So now we are going to begin with stereo-isomerism. So first of all, let us define stereo-isomerism. So this is going to be a phenomenon where we will be having compounds having the same molecular formula, but they will be differing in the spatial arrangement of atoms or groups. Now I'll be showing you the spatial arrangement of these atoms and groups, and then you will be understanding it better. But first of all, let us see what was structural isomerism. So in structural isomerism, for example, we have these molecular formulas and we draw the structural or the constitutional isomers for these. So we have C4H10, we can draw a butane, we can draw a 2-methyl propane for it. This is a 4-carbon chain, this is a 3-carbon chain, then 1 carbon as a substituent. Fine. Now, This is what type of isomerism? Well, this is chain isomerism because there is a difference in the length of the carbon chain. Then we have C3H711. This is one chloropropane and this is 2-chloropropane. What is the difference in them? Here we have chlorine at position number 1. Here we have chlorine at position number 2. So this is a difference in the position of the substituent. So this is position isomerism. Next we have C4H10O. Here we have drawn one butanol and diethyl ether. Here there is a difference of the functional group. So in all of these, what you can see is that the structural isomerism is a difference in the connectivity of atoms or groups within a molecule. 4 atoms directly joined to one another, 3 joined in one line and the other as a substituent. So they are differing in the connectivity of atoms or groups within a molecule, and the structural isomers, therefore, they are going to differ in order of connection of atoms. There is a difference in the order of connection. But now if I tell you that I have ethane, okay, can you draw any isomer for ethane? Well, you will not be able to. Why? Why will you not be able to? Because this is just 2 carbons. You cannot change the length of the carbon chain. And also these are only hydrogens. So what are you going to do? You cannot change the position and form a new structure. There is no functional group present. So you will not be able to draw any structural isomer for it. But if you talk about the position of these atoms, if I can vary them, what I will be getting is stereo-isomerism. What do I mean by this? Let us see over here. So I have this as a structure of ethane. Okay. So here you can see that we have 2 carbons and we have 6 hydrogens. So this is a molecule of ethane. Right. Now if you look at this way, what you can see is, can you see it? So can you see that I can vary the position of these? What I'm doing is I'm holding one carbon, okay, and I am rotating the bond so that the position of the hydrogens relative to each other, they are differing. In this position, you can see almost that one carbon is behind the other, one hydrogen is behind the other. But the moment I am rotating it, now you can see all the 6 hydrogens very clearly, right? Can you? And if I go back, you will not be able to see them very clearly. Fine. And if I make a proper angle, actually you will not be able to see the back ones also. These the angles may not be very nice also with the model. So just understand this, and I can rotate my carbon-carbon single bond and showed you different structures. Here you can see all the 6 hydrogens and here not. Fine. So the hydrogens at the back, they are being covered by the hydrogens forward. And if these two compounds, they are having some different properties, this means that this is going to be a type of stereo-isomerism. Okay, I hope this is clear. Now, this form and this form, both were having the similar connectivity of atoms. I had again same 2 carbons attached to each other. I have not changed them. The hydrogens, like 3 for the first carbon, the 3 for the back carbon, I have not changed their positions. What I am doing is just changing the orientation of these in space, and this is giving me different structures. So this is what we have as stereo-isomerism. Okay, I hope this is clear. With these models, it is going to be very easy for you people to understand. So next we have the types of stereo-isomerism. So we have 2 types of stereo-isomerism. One is conformational isomerism and the other is going to be configurational isomerism. The compounds, they will be called as conformational isomers and configurational isomers. Now what are these 2 types? First of all, both of them, they are stereo-isomers. So this means that if I'm talking about conformational isomers, They are going to be compounds which will be having the same molecular formula. They will be having the same structural formula also, but they are going to differ in the spatial arrangement of atoms or groups. Now, what is the difference? Let us understand this. So here the difference is going to be that the two compounds that we will be having a spatial arrangement difference, they can be interconverted into one another by the rotation of atoms about the sigma bond without breaking and remaking of bonds. So I showed you the model of ethane. So in this model of ethane, what I am doing is that I have one structure this, and the other structure I am having as this. Okay. So here what you can see is that the two structures, they are differing in the position of the hydrogens with respect to one another. And how I have made the structure different? I have just rotated the position of the atoms with respect to each other around the carbon-carbon single bond. Fine. So this is my carbon-carbon single bond. I am holding one carbon and I am rotating them, and I am getting different forms. So these forms, they are interconvertible by just rotating the atoms about the sigma bond. So this is what we have as conformational isomerism, and this we will be discussing a bit later on. Alright, so I will not be focusing more of your time on this. We will have a detailed separate lectures for what are going to be the possible isomerism, what are the difference in properties, everything we will be discussing in a separate lecture. So now we have configurational isomers. Now again, these are stereoisomers. So they will also be compounds having the same molecular formula. They will be having the same structural formula. They will be having different spatial arrangement of atoms or groups. But these stereoisomers, they cannot be interconverted without the breaking or remaking of covalent bonds. So this is what the difference is. They can be interconverted by the rotation of the atoms about the sigma bond, and they cannot be interconverted without breaking or remaking of bonds. So for these, we will not be having single sigma bond. What we will be having is some certain type of rigidity within the molecule, which is not allowing the two forms to interconvert. Okay. So this is something that we are going to just now talk in detail, because the configurational isomers, they are of two types. One is going to be geometrical isomerism and the other is going to be optical isomerism. So geometrical isomerism is what we are going to just now discuss. So you will be able to see by the stereoisomers that we are getting, they cannot get interconverted without the breaking and making of new bonds. Alright, so let us now understand what is geometrical isomerism. So configurational isomers, they are going to be of two types. One are going to be geometrical isomers, and then next they are going to be optical isomers. Geometrical isomers I am going to discuss in this lecture as well as in the next lecture, and after that we will be discussing in detail optical isomers. Fine, oh no problem. Now let us understand what is geometrical isomerism. So this is going to be a phenomenon where we will be having two compounds which will be having the same molecular formula, they will be having the same structural formula as well, but they are going to differ in the spatial arrangement of atoms or groups around the carbon-carbon double bond. Okay, now this is just the beginning of the lecture, so here we are talking about carbon-carbon double bond, but then as we move further, you are going to see certain more examples where along with carbon-carbon double bond, there is going to be geometrical isomerism present in some more type of structure. Fine. So, but we, for the start, we will be discussing carbon-carbon double bond so that you have a complete understanding. Fine. Now, why is there a difference in the spatial arrangement of atoms or groups around the carbon-carbon double bond? First of all, let us understand this. So, we have a carbon-carbon double bond being made by a sigma bond and a pi bond. And around a carbon-carbon double bond, we have a restricted rotation. When we have a carbon-carbon single bond, you have seen that if I just take hold of one carbon, I can rotate the position of the atoms by rotating the single bond. It is very easy for me. But when I have a double bond, so this is my structure. If you see, here we have between the two carbons a double bond. When I have a double bond, you can see that it is not easy for me to rotate it. I have one, I am trying to rotate the double bond, but I am not able to. So this is a restricted rotation. This restricted rotation is because of the presence of the double bond. Now, why is it this so? Let us understand this also. So we have a when we have a carbon-carbon double bond, let me draw. For example, we have ethene. Okay. So this would be my structure for ethene. In this structure, what you can see is that we have this to be a sigma bond, a sigma bond, a sigma bond and a pi bond. For one carbon, we will be having 3 sigma bonds and we will be having 1 pi bond. What is the hybridization when we have 3 sigma bonds? It is going to be sp2 hybridization. When we have sp2 hybridization, what does that mean? The geometry is going to be trigonal planar geometry. All the atoms, they are going to lie in one plane and all the bonds, they are in one plane. Fine. And the atoms, they will be forming the corners of a triangle. So if you look at this structure, right, this is my carbon I am talking about. So this to this to this. So these three, they will be forming a triangle and all of them, they are going to be in one plane. Now, how do you understand this? You see over here. Fine. So if I keep this over here, well, you can see all the atoms, they are touching each other. Fine. Sorry, they're touching the tray. So these are all in one plane. I can keep it at like, sorry. I can keep it like this. This is going to be on one plane. Fine. So this, they are on the equatorial plane, all the bonds, right? They are all coplanar. Now this is sp2 hybridized orbitals. But after that, the carbon atom is going to be left behind with one unhybridized orbital also. And this unhybridized p orbital of carbon, this is going to lie at a 90-degree angle to the plane of the equatorial plane where we have all these bonds, and this is going to form a pi molecular bond with the adjacent unhybridized p orbital of another carbon atom. Let us try making this also. Okay, so just imagine now this is my structure. Here I have one sigma bond. Okay, and the pi bond, how is it going to be formed? It is going to be formed when I have the unhybridized orbital. This I have drawn, made with clay. All right. So these are the unhybridized orbitals of the two carbon atoms. You can see. Now these are at 90 degree to the plane of the bonds. Right. So this is at 90 degree. Now these two unhybridized orbitals, what are they going to do? They are going to form a pi electron cloud over both the carbon atoms, over both the carbon atoms, which is going to be the plane of the hybridized orbital. So there is one pi electron cloud. If you see the diagram, so this is diagrammatically, you will be having a pi electron cloud above and below the plane of the sigma bonds, right? So if you look back over here, this one, fine. So you are seeing this. This is the structure that we are having. Sorry, this has to go at 90 degree. Now, you can see this is at 90 degree. Now, when these are 90 degree, they are overlapping with each other. Now, what will happen if I change now? If I try to turn a bond, what will happen? These two, they will not remain parallel to each other. They will get disturbed. The geometry will get disturbed. And when they are not going to be parallel to each other, the effective overlapping between them, this is not going to happen. When this will not happen, the molecule will become unstable. So if you just see these, okay, so this is when we will be having an effective overlapping. If I change this angle, they are not going to overlap with one another. And when they are not going to overlap with another, we will not be having a pi bond formation. Is this clear? So what you will be having is, because of this restricted rotation, the pi bond is present. We are not able to change the position of the atoms. So this is the position I have atoms in this structure. Fine. So here what you can see is that we have the two carbons, the two hydrogens. If I put it this way, you will be able to see the position. You have the two hydrogens on top and you have the two chlorines below. This is the position. Fine. Now what I do is, because there is a restricted rotation, if I show you one more structure, in this what you can see is, right, now I have again this double bond. I have one hydrogen above and one chlorine above and one chlorine below and one hydrogen below. So this structure, this is different from this, is it? But what is the name of this compound? This is 1,2-dichloroethene and this is also 1,2-dichloroethene. But what I have is a difference in the spatial arrangement of atoms. Are you understanding? Here the hydrogen is opposite the hydrogen, a chlorine is opposite the chlorine, and in this structure the two hydrogens, they are above the carbon-carbon double bond, the chlorines are below the carbon-carbon double bond. And you can see a difference in the spatial arrangement of atoms. As far as the linking is concerned, as far as the structural formula is concerned, that is the same. Clear? Right? Alright. So now if you look over here in this figure, so you can see that we have the two carbons forming the carbon-double bond. These two X atoms, they are on one side and the two Y atoms, they are on the other side. In this structure, you can see that the X's, they are diagonally opposite to each other and the Y's, they are diagonally opposite to each other. So this is going to be called as a cis-isomer. This is called as a trans isomer. Now, what do we mean by that? Again, you can see over here. So we have carbon-carbon double bond. What we are saying is that these two atoms of the same kind, they are above the double bond. The same kind, they are below the double bond. So we have two same kind of atoms on the same side of the carbon-carbon double bond, as you can see over here in the diagram. So X and X on same side of the carbon-carbon double bond. This is what we call as a cis isomer. And when they are opposite, when they are diagonally opposite to each other, as you can see in this structure, we will be calling it as a trans isomer. Okay. So the story was, as the write-up was concerned, that we had the overlapping of the unhybridized p orbitals. This is going to be maximum when they are going to be parallel to one another. If we are going to change the carbon-carbon double bonds, we are going to just try to twist it like we did for the single bond. Well, we will be making a change in the coplanar geometry. The pi bonds, they will not remain parallel to one another and there will be not an effective overlapping. This is going to make the molecule unstable. Thus, the rotation of the groups around the carbon-carbon double bond, this is restricted. I hope now you have got all this, right? So this is clear. Very good. So the two different spatial structural arrangements, they are not easily interconvertible. What I have to do is, if I want to convert one form into the other, I will have to break the bonds. Fine. Or either I have to make the break, actually I have to break the double bond. So you just look here, what I'm doing is that I break the bond and I remake it. Fine, and I have got the other structure. Want to get that back? Again break the two bonds, remake the two bonds by changing the position and we get back the cis structure. So we have to break the bonds, make the bonds back again to get the structures which we were having differently. So we have two different spatial structural arrangements which are not easily interconvertible. We cannot convert them into one form into the other without the breaking of bonds and the making of new bonds. So these are two separate different structures which will be having different properties. Okay, is that clear? So the two structures are, one is a cis isomer when we will be having two atoms of the same kind on same side of the carbon-carbon double bond, and when they are going to be opposite to each other, opposite side of the carbon-carbon double bond, diagonally opposite you can say to each other, this we will be calling it as a trans isomer. Okay, want to see them once again. So this is the trans isomer, this is going to be the cis isomer. Clear? So now we are going to study in detail about all these. What are the conditions essential for geometrical isomerism? What are the characteristics for these compounds and so on. So let us now learn more about them. So now how are we going to recognize whether the compound is going to show geometrical isomerism or not? So I'm going to teach you certain things over here which are going to be very important. Alright. So the first thing is that there should be some restricted rotation present in the molecule. If there is some restricted rotation present, the molecules they will not be able to convert into one another, and therefore we will be having a different type of compound. Okay, we will be having isomers which are having a different spatial arrangement. So the compounds which are containing a carbon-carbon double bond, they do have this restricted rotation, and that is why we see geometrical isomerism in these compounds. So there must be two different groups on the left hand carbon and two different groups on the right hand carbon. Alright, so here you can see this is carbon number 1. It has two groups X and Y, and this is carbon number 2. This also has groups X and Y. The two groups on each carbon, they should be different. They should not be the same. Okay, so for example, if you look over here, this carbon, this has two X's, this carbon 2 has two Y's. So this is a structure which will not be showing geometrical isomerism. Just remember this. This will not show, this will show. And when we have two groups which are on the same side of the carbon-carbon double bond, well then this will be a cis isomer, and when they will be on opposite side, well we will be calling it as a trans isomer. Another thing is that it is not essential that the left hand groups they have to be the same as the right hand ones. So for example, if you look over here, we have on this carbon a X and a Y, and on this carbon a Z and an X. So the Z X's you can see that both carbons they have, but the carbons now they are differing in these two groups. There is Y on one side and a Z on one side. So this structure is also going to show geometrical isomerism, and as the two X's you can see over here, they are diagonally opposite to each other. This is going to be a trans isomer. Had it been on the same side, we would have called it as a cis isomer. Alright. Now another possibility is that all the four groups they are different. When all the four groups they are different, well we will be still having geometrical isomers, but now we will not be able to call them cis and trans. Okay. So we have A, B, C, D all different. So geometrical isomerism, essentially you should have a carbon-carbon double bond and each carbon should have different groups attached. But this will not be a cis and trans isomer. Here we will be learning a new system, and that will be called as the EZ notation or EZ nomenclature for geometrical isomerism, that we will be doing a bit later. Okay, I hope this is clear. So to sum up, what are the conditions essential for geometrical isomerism? Number one, that their molecules, they must have some form of restricted rotation. For example, a double bond. For example, we have a carbon-carbon double bond. There are going to be certain more examples coming up and you will be learning all of them. So just remember that the molecules, they must have some form of restricted rotation. Alright, and the next is that if we have a carbon-carbon double bond, then there should be two different groups attached to each carbon atom. So now let us look at a few examples. So first of all, here you can see this structure. This is cis-but-2-ene. Why do we call it as a cis structure? Because here first of all we have a carbon-carbon double bond, and then we have each carbon having two groups. One is a CH3 and a H, and in this structure you can see both the CH3 are on the same side of the carbon-carbon double bond. The both hydrogens they are on the other side. Alright, so this is a cis structure, and when we will be drawing the trans structure for it, the two methyl groups now they are diagonally opposite to each other, and the two hydrogens they are diagonally opposite. Alright, I hope this is clear. Let us see one more example. So this is cis-1,2-dichloroethene. where we have two chlorine atoms on the same side and two hydrogens on the other side. And when they are going to be diagonally opposite, we will be calling it as a trans structure. Next, we have a structure where we have two carboxylic acid groups on the same side. So this is going to be a cis structure. What is the name of this compound? Well, it is written over here. This is malic acid. Okay, so this is the common name for the structure. What is the IUPAC name? Well, we have a 4-carbon chain. So this is bute. All right, bute, and we have a double bond at position number 2. So bute 2-ene, and we have 1 and 4 dioic acid. So this is bute 2-ene 1,4-dioic acid as far as the IUPAC name is concerned, and this is a cis isomer because the the two functional groups, you can see they are on the same side of the carbon-carbon double bond. If they are present diagonally opposite to each other, we will be calling it as a trans structure, and the common name for this compound is fumaric acid. So this is malic acid, this is fumaric acid, and please do remember this very well because this comes many times in the examination, that malic acid and fumaric acid, what type of isomerism do these show? Okay, or malic acid is a dash geometrical isomer, fumaric acid is a dash geometrical isomer. So malic acid is a cis geometrical isomer, and this is a trans geometrical isomer. So these are certain things that you have to remember. Alright, I hope this is clear. Now the next thing that you see is that if you see the cis-bute-2-ene, we find that the boiling point is 4 degrees Celsius, whereas the trans compound, this is having a boiling point of 1 degree Celsius. So the cis compound is having a higher boiling point than the trans compound. The next you can see for dichloroethene, the cis structure, this has a boiling point of 60 degree, a melting point of minus 80 degrees Celsius, and the dipole value of 1.85 dpi. Whereas the trans structure, this is having a boiling point of 48 degrees Celsius, a melting point of minus 50 degrees Celsius, and the dipole moment value, this is coming as 0. So the the boiling point for the cis structure is higher. The melting point for the trans structure is higher, and we have a dipole moment value for the cis and a 0 value for the trans. Okay, and now in the next example also you can see that the melting point for malic acid is 130 degrees Celsius, whereas for fumaric acid this is 287 degrees Celsius. Okay, so what are you seeing over here is that the boiling points for the cis structure, that is higher, the melting point is higher for the trans structure, and the dipole moment values for the cis compound is going to be some value, whereas for the trans compound you will be seeing that either the value is going to be very small or it is going to be 0. Okay, so now why do this happen? Let us understand. So now let us understand why the cis isomers, they have a higher boiling point. So if you look at this example, we have cis-1,2-dichloroethene, and in this structure what you can see is that the two chlorine atoms, they are on the same side of the molecule, and the two hydrogens, they are on opposite side. So this is a cis structure. Now in this cis structure what you can see is that the two chlorines, they are on one side, and each chlorine atom, this is more electronegative than the carbon. So the chlorine atoms, they will be having a partial negative charge, and if you compare the whole molecule, although carbon and hydrogen, they have the same electronegativity values, but we have an electron pull towards chlorine, so you will be experiencing that on this side of the carbon-carbon double bond we have a partial negative charge, and on the other side we will be having a partial positive charge. Therefore, what has happened? We have created a polar molecule. There are dipole-dipole interaction present in the molecule along with the dispersion forces. Okay, so between molecules there are going to be present dispersion forces anyways, but now we have dipole-dipole interactions also, and these are going to require now extra energy to be overcome, and hence the boiling points, they are going to be higher. If you look at the trans compound, again you are going to have polar bonds. A carbon chlorine bond is going to be a polar bond. The partial negative charge is going to be on the chlorine atom. There will be partial positive charge on the hydrogen, but what you will be seeing is that the whole molecule, this is going to be a non-polar molecule. Why non-polar? Because the partial positive charge on the hydrogen on the top is being balanced by the positive partial charge on hydrogen below. So these two, they are going to cancel out each other. Similarly, the partial negative charge on the chlorine is going to balance the negative charge on the chlorine. They are opposite each other. So as a result, the molecule, this becomes non-polar. Okay, and therefore we will be having a cis compound having a higher boiling point than the trans compound. Now with these two examples of cis 1,2 dichloroethene and trans 1,2 dichloroethene, let us understand that why the melting points of cis isomers, these are lower than the trans isomers. So here what you have to remember is that in order for the intermolecular forces to work well, the molecules should be able to pack together efficiently in the solid. Better is going to be the packing in the solid. Stronger are going to be the intermolecular forces of attraction. And then we will have to require more energy to break those intermolecular forces, and we will be having higher melting points. Okay. So to have higher melting points, we need to have more intermolecular forces, and for more intermolecular forces, we need to have a better packing of the molecules in the solids. Okay, that is clear. Now what you can see is that the cis isomers, they are not as good in the packing as the trans isomers, because this is a symmetrical structure. This is somewhat of a straight shape, whereas this is of a U sort of a shape. Okay, so essentially you can just understand it that this is an unsymmetrical structure, this is a symmetrical structure. A symmetrical structure gets packed better than an unsymmetrical structure. Okay, this is one thing. So the packing, if it is going to be poor in the cis isomers, this means that the intermolecular forces, they will not be very effective. Therefore, we will be needing less energy to melt the molecule, and hence we will be having a lower melting point for the cis isomer. And in the trans isomer, the packing is better, so the intermolecular forces of attraction, they are better, and we will be requiring more energy to break those forces. And the trans isomer, this will be having a higher melting point. Alright, I hope this is also clear now. So now let us sum up this discussion into the characteristics of geometrical isomers. So the first thing, the geometrical isomers, they have similar chemical properties. Why similar? Because they have the same functional group. What will be different in these isomers? Well, the rate of the reactions, they will be different. Okay, but otherwise the chemical properties, they will be similar because of the same functional group. The next, they will be having a difference in physical properties. So they are isomers, so they will be having some difference in properties. It is going to be a difference in the physical properties. The melting point, the boiling point, the dipole moment, the refractive indices, they are going to be different, and therefore we will be classifying them as cis and trans isomers. The cis isomers, generally they have lower melting point, higher boiling point, and higher refractive indices. The cis isomers, they have higher dipole moments. You have seen that also, that it is because of the unsymmetrical structure of these isomers that they have high dipole moment values. And because they have high dipole moment values, so they have higher boiling points. The trans isomers, they fit well into the crystal lattices because of their similar structures. So we will be seeing that the trans isomers, they have high melting points, right? And high melting point because high crystal energy. A crystal has been formed well because of a better packing, and therefore we are going to require more energy to break that crystal lattice. Okay, so I hope now everything is perfectly clear with you people. You have no doubt at all. So to sum up, I have put up a table also for you so that you can remember it easily while you are going to revise your lectures. So the melting point for the cis isomer is going to be lower than the trans. The boiling point is going to be higher. The solubility for the cis isomers is higher than the trans isomers. The refractive index values is going to be higher for the cis comparison to the trans isomers, and the dipole moment values for the cis isomer is going to be appreciable because the dipole moment of the individual bonds, they are not going to cancel out each other, whereas in the trans isomers it is either going to be a zero dipole moment value or this can be negligible. When is it going to be negligible? Well, it is going to be some value if, for example, you have a structure like this. Okay, so if you have a structure like we have a Cl over here, H, let us say it is an OH, and this is a Cl. Okay, so these two now they are going to cancel out each other, but because of this now this is a different group over here, so these will not be cancelling out each other. Okay, so you can have some dipole moment values for the trans structures. It is not essential that it has to be a zero. It will be zero when you will be having identical groups opposite each other. Okay, I hope this is also now clear to you people. Now the next thing is that please do remember very importantly that geometrical isomerism is not going to be shown by compounds which have a carbon-carbon single bond, because around a carbon-carbon single bond, even if we have different groups, the atoms they can have a free rotation. So if they have a free rotation, well, they are going to be interconvertible, and what we require is a restricted rotation so that we have specific different structures, the cis isomers and the trans isomers. And another thing is that the carbon-carbon triple bond, if it is present, well, these structures they will also not be showing geometrical isomerism, because these structures they are going to be linear structures. Okay, so they are going to be one line structures. You will not be seeing anything in space that is going to be different. Okay, good. Now that you have understood what is cis-trans isomerism, I have a question for you. And the question is that you have to name these compounds. Alright, first of all, you have to name these two compounds, and then you have to tell me which is a cis isomer and which is a trans isomer. Can you tell that? Well, you will not be able to tell. Why you will not be able to tell? You will not be able to tell because there are four different substituents on the two vinylic carbons, right? So the two carbons you can see, one is a bromine, a chlorine, a methyl group and a hydrogen. All of them, they are different. As far as the name of the compound is, this is 1-bromo-2-chloropropene, but you cannot tell whether it is going to be a cis isomer or a trans isomer looking at these structures. So here is going to be a learning of a new nomenclature system, that is the EZ system of nomenclature, and this is the system which is preferred in fact by the IUPAC system, because here we can name any alkene isomer with this system. Okay, so what is done is that the relative priority of the two groups bonded to one of the carbons is determined, and then the relative priority of the two groups bonded to the other carbon, they are decided. Now what do I mean by that? Let me explain you. So this is a system of nomenclature of alkenes. This is a system for specifying the double bond stereochemistry based upon an atomic number criterion for ranking the substituents on the doubly bonded carbons. So with the help of this atomic number criteria, we are going to rank the various groups present on the two carbons, and this is going to help us give the spatial arrangement of those atoms on the two carbons. Okay, so what we will be doing is that we will be seeing where the atoms of a higher atomic number they are present. When the atoms of the higher atomic number they are present on the same side of the carbon-carbon double bond, we say that the double bond this has a Z configuration, which is going to be just similar to the cis configuration, right? Cis means same side, so here Z is going to be in same side, and Z here this stands for the German word zusammen, which means together. And then we have, if the atoms of the higher atomic number they are on the opposite side of the double bond, they are going to be diagonally opposite to each other, then we will be saying that the configuration is E type, and here E word this stands for the German word entgegen, which means opposite, right? So cis is going to be similar to Z and trans is going to be similar to E. Here we will be having the atoms of higher atomic number on the same side, and here we will be having the atoms of the higher atomic number opposite to each other, diagonally opposite. Okay, so let us see this with the help of an example. You will understand better. So here you can see that this carbon, this has a chlorine and a hydrogen. Out of these two, which has a higher atomic number, it is chlorine. And on the other side, the carbon, this has a bromine and a fluorine. So which is of a higher atomic number? This is a bromine. So now you can see that both of these, chlorine and bromine, these are our groups of higher priority. Okay, so they are a group of higher priority because they have a higher atomic number. And now because they are on the same side of the carbon-carbon double bond, this is going to be a Z configuration. And now in this structure, what you can see that again we have a chlorine and a hydrogen. A hydrogen is going to be of a lower priority, chlorine is going to be of a higher priority because the atomic number of chlorine is higher. Okay, similarly fluorine and bromine, bromine is of a higher priority, and now you can see that both of them, they are diagonally opposite to each other, so this is going to be a E configuration. Okay, so this is a trans, this is a cis now, but we do not use a cis and trans for them. We will be calling this as a Z configuration, we will be calling this as a E configuration. Okay, no more cis and trans for them. Alright, and this we can use for any type of alkene. If it is having two groups of the same kind, it is having two groups of the same kind, and these two, they are different. So for all of these alkenes, you will be able to use this nomenclature. So now what is important in this easy system of nomenclature is we have to set the relative priority of the groups which are attached to the carbon-carbon of the double bond. So we will be learning certain rules to set these relative priorities, and the rule number one is that the atom with the higher atomic number, this has a higher rank. Right? So if you look at this example here, you can see that we have four different groups attached to the two carbons, and this carbon, this is attached to a hydrogen and a bromine, which is having a higher atomic number. I've written down the atomic numbers, but I think you should be knowing these atomic numbers yourself by now. So we have bromine with the atomic number of 35 and hydrogen with the atomic number of 1. So bromine is of a higher atomic number, so this will be of a higher priority. And then we have chlorine and we have carbon. We are not going to total out the atomic number of all these. You are going to see the atom which is attached to the carbon of the double bond. Alright, so to the carbon of the double bond, we have a carbon attached, and the atomic number of carbon is 6, and that of chlorine, this is 70. So which is a higher priority? It is going to be chlorine. And now you can see that both these high priority groups, they are present on the same side of the carbon-carbon double bond. So this is going to be the Z isomer. And when you can see that these are opposite to each other, then this is going to be the E isomer. Okay, I hope this is clear. Let us learn the rule number 2 now. Now look at this example over here, and then you have to choose which is the Z isomer and the E isomer. The names are already given to you, but let us understand them, how we are naming these compounds. Alright, so here what you can see, in this carbon, this is attached to a methyl group and a hydrogen. So the first point of attachment to this carbon, this is a carbon. Alright, and then this carbon is attached to hydrogen. So we are looking at the carbon and the hydrogen which are directly attached to this carbon. So carbon, this has a higher atomic number, so this is going to be group of higher priority. Now on the other side, what you will be seeing is that we have a ethyl group and we have a methyl group attached to the carbon. Right, the groups, they are different, okay, but now what you will be seeing is that this carbon, the first atom that is attached over here, this is the carbon of the ethyl group, and on the other side we have a carbon of the methyl group. Now, because both of them, they are carbons, how are we going to choose which is a group of higher priority? You can see that the ethyl group is a higher priority group, but why? So we have a rule for that, and the rule says that if two substituents bonded to a carbon, they start with the same atom, there is a tie, as we have a tie of the two carbons over here, then we will be looking at the second, the third or the fourth atoms away from the carbon of the double bond until we reach the first point of difference. Okay, so if we elaborate this structure over here, what you will be seeing is, I will be drawing this side only where we have a controversy. So this side we have a carbon, this side also we have a carbon. So this is same. So we have a tie. Let us look at the other. So to this carbon, we are going to form 3 more bonds. This is a H and a CH3 which is attached to this carbon, right? A CH2, CH3. And on the other side, what do we have? We have a hydrogen and a hydrogen. So can you see now to this carbon, we have a hydrogen. We have to this carbon also a hydrogen, a hydrogen, a hydrogen. But now this third one, this is a carbon and this is a hydrogen. So which is a group of higher priority? Because of this carbon, we will be having the ethyl group to be a group of higher priority. Okay, I hope this is clear. Just let me rub it out and then you will be able to see this in writing also. So a C2H3 substituent and a CH3 substituent, they are equivalent by rule number 1 because both have carbon as the first atom. By rule number 2, however, the ethyl ranks higher than the methyl because ethyl has a carbon as its highest second atom, whereas methyl has only hydrogen as its second atom. Okay, so these two now they are on the same side, so this is going to be the Z isomer, and when they are going to be opposite to each other, this is going to be the E isomer. We can do one more example to make the concept better. So let us look over here. So here now what you can see is this side we have a carbon and a CH2Cl, and this is a Cl. So the point of attachment to the carbon is a carbon and a chlorine. So this is a chlorine will be a group of higher priority. Alright, on the other side we have a CH2OH, and this we have a CH3CH3. Okay, so which is the atom which is attached to directly to the carbon? It is this carbon and this carbon. So again we have a tie with the two carbons. So then what do? We look at the three carbons, three groups which are attached to the carbon. So we have a CH3, okay, and then we have a H and we have a CH3 attached to the first carbon. I am talking about this carbon now. Okay, so this is the structure I am drawing for this one. And for the other side, if we draw this one in an elaborate way, you will be seeing that it has two hydrogens and one is a OH group. Okay, so out of these what you will be seeing is that this carbon is attached to carbon, hydrogen and carbon, and this is attached to a hydrogen, oxygen. So out of all the three attachments to the carbon, we can see the highest is a carbon, and here from the three attachments the carbon has the highest is an oxygen. So which is going to be the group of a higher priority? CH2OH. Okay, I hope this is clear. All the three groups that were attached to the carbon, we are seeing the second atom. Okay, and whichever is going to be of a higher atomic number, that group we will be choosing as a high priority group. So out of these now, chlorine and CH2OH, they are of higher priority. They are on the same side. So this is going to be the Z isomer and this is going to be the E isomer. Okay, clear? Good. Now the next rule is rule number 3, and this rule is going to be the most important rule for you people. Please do be very attentive in understanding what I am going to explain you now. If you do not understand it, well, you're bound to make mistake in the EZ system of nomenclature. Alright, so the rule says that if we have an atom which is forming a double bond or if it is having a triple bond, so this rule is going to be applicable over there. So if an atom is making a double bond to another atom, the priority system treats it as if it was singly bonded to two of those atoms, and if it is making a triple bond to another atom, then the priority system treats it as if it was singly bonded to three of those atoms. Now what do I mean by this? For example, we have an aldehyde group. So in the aldehyde group, we have a carbon forming a single bond with hydrogen and a double bond with oxygen. So the double bond with oxygen, how are you going to treat it? You are going to treat it equivalent to being a carbon atom which is forming two single bonds with two oxygen atoms. Okay, let me explain you by drawing it, and you will be able to understand this better. We have a CH and a double bond O. So how are you going to treat it? You are going to treat it as if the carbon is making two single bonds with the oxygens, and this is the hydrogen. Now please do remember one of the atoms, this is a real atom which is actually there. We never had two oxygen atoms, we had only one oxygen atom. So this one is an imaginary atom, this is a phantom atom, this is a pseudo atom, whatever you may call it, but this is not existing actually. So we are going to put it into a bracket so that you can understand the difference between a real atom and the phantom atom. Okay, now remember one more thing over here, that this carbon is making a double bond with oxygen. So you have made a carbon with two oxygen atoms by single bonds. Even this oxygen is also making a double bond with the carbon. But the real oxygen atom, you have still not made two carbons with that. So you have to make one pseudo carbon for this oxygen also. one pseudo oxygen for the carbon and one pseudo carbon for the oxygen. This is what will make the double bond proper way to be represented by the single bonds. Okay, let me give you one more example. You will be understanding better. If you have a COOH group, so in the COOH group you have a carbon bonded to oxygen by a double bond and a COH, right? So here how are you going to represent it? We have a carbon, a oxygen, double bond, so another oxygen by a single bond, and this is the OH. Okay, so out of these two oxygens, one is a real and the other is phantom. The real oxygen is also making a double bond with the carbon, so we will be making a pseudo carbon for this oxygen as well. So this is how you are going to represent your structure. Okay, so if I give you an example, the more you practice, the better you will be. But please do understand this. This is going to be very important, and otherwise you are going to get confused if you do not do this. Fine. So for example, you have a carbon carbon triple bond now. So how are we going to represent it? We have a carbon bonded to a nitrogen. We have three bonds, so we will be making the three bonds. We have three bonds with nitrogen, so we will be making three nitrogens. Only one of them is real, the rest two are imaginary or phantom, right? So we will be putting them into bracket. Now this nitrogen was also making three bonds with the carbon, so we have to make the nitrogen also with three bonds to the carbon. So this nitrogen, which is the real one, this is also going to make two more bonds with carbons. But these two ones, they are the imaginary ones. Okay, the original one is only this carbon and nitrogen. Fine. So when you will be choosing your groups, you will be seeing this order also. Okay, when you will be doing the examples, you will be understanding it better. So let me give you now an example. So how you are going to draw it? Fine. So now if you have this as an example, here you can see that there is a triple bond present and there is a double bond present. So we are going to expand it this way. And why do you need that expansion? So here you can see that we have a carbon bonded to carbon carbon. So they are the same groups. So it is going to be a tie. So you have to move on to the next one. When you move on to the next one, this was my carbon. This is a CH2OH. So C, two hydrogen and one OH. So this is how I represent this one. And when I represent this one, because it's a triple bond, so I have my carbon. This is my original carbon with its hydrogen. Fine. And then we have a triple bond. So we will be making two bonds with the carbon. But these are my imaginary ones. Fine. Now if you look at this carbon, let me just make it in this one, the real one, right? So how many bonds it is making? This is making one bond here and one bond here. So this is making two bonds. This means that its two valencies, they are still not satisfied. How are we going to satisfy them? We are going to satisfy them with the pseudo carbons over here, right? I hope now this is clear. So this is how you are satisfying the valencies also, and both the carbons which were forming a triple bond, now both of these atoms, they are forming a triple bond. Okay, triple bond being represented by three single bonds. Similarly, if you look at the opposite side, I will expand this structure over here. So you will be having a C, a H, a CH2, right? This is my actual, and then I have a double bond, so I will be making one pseudo carbon. This will be my pseudo carbon. Fine. Now this carbon was also making a double bond, so I have to make a pseudo carbon for this one also. So I will be making a pseudo carbon for this one also. Now you will see that for this real atom, I am satisfying all its four valencies by one carbon, 2, 3 and 4. Okay, so this is how you will be representing it, and then you will be able to choose the priority. Now when you choose the priority over here, you can see that we have a hydrogen and an oxygen. I can just write it in short as a OHH. Okay, and when I see over here, these are a C, C and C. So my atom which is having a higher atomic number is oxygen, so my priority group is going to be this one. And for the CH double bonded to CH2, what is going to be my priority? You can see over here, this is a C, C and a H. And if you look over here, this is going to be a H, H and a C. So here we have two hydrogen, here we have two carbon, so this is going group of priority. Fine. When they are opposite to each other, it is going to be an E isomer, and when they are going to be on the same side, it is going to be the Z isomer. Okay, I hope this is clear. This is very important, and this is going to be very helpful to you in using any nomenclature question. You will be seeing it in the next example, where you are going to even get stuck up if you do not make these pseudo atoms. Okay. So let us move further to rule number 4, where you will be seeing that example I am referring to. So rule number 4 is for the isotopes. Now why do we need a rule for the isotopes is because the isotopes, they are atoms with the same atomic number, and here in the EZ system the criteria that we have taken to choose the priority group is atomic number. So if we have isotopes as one of the groups, then which one is going to be of higher priority? When both of them, they will be having the same atomic number. So here we will be changing the priority rule. The isotopes, we all know that they have different mass number. So we will choose the mass number to determine the relative priorities of the groups attached to the carbons, right? So when different isotopes of the same element, they are compared, for example, we are comparing deuterium and protium, the heavier isotope is going to be ranked higher than the lighter isotope. So we have the atomic numbers. So you see for the atomic numbers, both the isotopes, they will be having atomic number as 1, but the mass number is different. So which one will be having a higher mass? That is going to be our group of priority, right? For example, you can see we have a D and a H. So the D, deuterium, this is going to be our group of priority. Now on the other side is what I want you to see once again. This is very important. Alright. So this is actually the learning that you have to do. The rest, even if you look at the books, you will be able to understand. This is one thing that you will not be able to understand. Fine. So if you write this CH, you see first of all we have a carbon. So this carbon of the double bond is attached to two carbons. So we have a tie. So we have to move further. When we move further, this is the CH2, which we have drawn previously also. So this is a hydrogen. This is the carbon with which it was making a double bond, but now it cannot make a double bond, so it will be making two single bonds. One which we have repeated is going to be a phantom carbon. So we have put it into bracket. Now the real carbon, this is also making, this one is also making a double bond. So we will be making a phantom carbon for this also. Okay. Now after you have done that, just complete all the valencies with the hydrogen, right? So this carbon is already making a double bond. So here we have the 4. This one was a C double bond 4, right? So this carbon, this 4 valencies are satisfied. For this carbon, you can see 2 satisfied. So you will be writing a H and a H. And for this carbon, it is just 1. So you will be writing a H and an H. Okay. Now if you look at this one, what you will be seeing is this is a CH3 and a CH3. So here if you look, you can see that a H and an H, a C and a C, a C and a C. So our second atoms, they are also having a tie. So we have to move further. When we move further, now what you can see is that this, you can see that this is a H, H and C. Okay. So out of these two, which is going to be a higher priority, this is going to be this group. So we have a carbon here. Here what you can see, these are all hydrogens. So the group which is going to be of a higher priority is this at the third level. And that is only when you made this pseudo carbon. Had you not made this pseudo carbon, you would have got puzzled up what has happened. Fine. So this is why it is very important to make the pseudo carbons very well. Okay, I hope you have got it very well. You will not make a mistake in your examination. I can give you one more example if you want. Let us see that. All right. So if we do one more example, what you have is, for example, we have a carbon-carbon double bond. On this side, we have one CHO group and the other we have a COOH. Fine. So how will we write this? Well, when we write this, the CHO, I'm just rubbing it out so that we can expand it. So we have a C, we have a H, a double bonded oxygen, so making two single bonds, one real and one phantom. Now this oxygen was also making a double bond, so we have a phantom carbon also. So this is how you draw this. And for the COOH, how you will be doing it? So for the COOH, you will be doing a OH, a double bonded oxygen again, a double bonded oxygen again. So this one was my real, this one was my phantom. Fine. So the real one, I will be making one more phantom carbon with this. So here now you can see that we have a OOH and we have a OOO. So you will be able to settle down on the second level only, that this is going to be our group of priority. So the carboxylic acid group is going to be of a higher priority than the aldehyde group. Okay, so this should be clear now to you people. Do not make a mistake, please. So now you have learned Cis-Trans geometrical isomerism. You have learned EZ system of the nomenclature for geometrical isomerism. And now we have the last one. This is Syn-Anti isomerism. But this is not going to be the end of geometrical isomerism. We have still more to study. And I will be taking one more lecture of yours. That will be the next lecture, where we are going to discuss geometrical isomerism in cyclic compounds. And that is also going to be very important. Fine. Now, as far as the Syn-Anti isomerism is concerned, well, you all have seen the compounds where they have a carbon-carbon double bond structures exhibiting geometrical isomerism. Now we have a carbon nitrogen double bond. So the compounds which contain carbon nitrogen double bond, they can also show geometrical isomerism. And these compounds, they are going to be aldoxymes and ketoxymes. Why do they show geometrical isomerism? This is again because of the restricted rotation around the carbon nitrogen double bond. So if you look at this one example, this is benzaldoxime. So here what you can see is that we have a carbon forming a double bond with a nitrogen. So the necessary condition for the carbon to exhibit geometrical isomerism was that it had to have a double bond, which is a restricted rotation, right? And then the two groups which are attached to the carbon, they should be different. So you can see over here, one is a H and the other is a phenyl group C6H5. Now on the other side, we have a nitrogen. Now on nitrogen, we have only one group. So how is it going to show a geometrical isomerism? Well, here what you are going to remember is that nitrogen, this has one lone pair of electrons. And this lone pair of electrons, this is also present in an orbital, right? So this is all again, it is going to be an electron density area. So we are having two groups around nitrogen, you can say. One is a OH group and the other is a lone pair of electrons. So for nitrogen, you will always be seeing just one group. Okay. So we are going to see Syn-Anti isomerism, where we will be having a carbon nitrogen double bond. The two groups of atoms around the carbon atom, they have to be different, and nitrogen, obviously this will be having just one group, so it is going to be different from the lone pair of electrons. Okay, so this is going to be the condition for Syn-Anti isomerism. Now you can see this structure and you may be finding it difficult how you're going to remember this structure. So let me give you first of all a reaction how an aldoxime is formed, and then it is going to be very easy for you people to study the structure, remember the structure, and then the geometrical isomerism. This is a reaction that you will be learning in class 12. So I'm not teaching you anything extra. It is only that I'm teaching you a bit earlier. Fine. So what we have is an aldehyde. Okay. So I have a carbon, a hydrogen, a double bond. This is a CHO group. To this I am putting an alkyl group. It can be any alkyl group. For example, over here you are seeing this is a C6H5. Fine. So it can be any alkyl group. It can be a CH3. It can be a C2H5. It can be a phenyl group. Fine. Now the next, this is going to react with hydroxylamine. Hydroxylamine has the formula NH2OH. Okay. Now why I have written this H2 ahead of the nitrogen is because when these two, they are going to react with one another, there is going to be a release of a water molecule in this way, right? So the oxygen goes out from the aldehyde and two hydrogen go out from the hydroxylamine. And if you now just simply join these two structures by what all is left behind, this is a C and a H and a R. The double bond is left behind. Very simple to understand. The oxygen has only gone out. The mechanisms I'm not teaching you. I'm just teaching you how you're going to write this formula and remember this. Okay. So we have now a nitrogen, and on the nitrogen, what is left behind? An OH group. And the nitrogen, this has its lone pair of electrons. So you can see this is a resemblance to the structure. Okay. So I hope now you will remember how you're going to make this structure. And then you can show the Syn-Anti isomerism in it. Now for Syn-Anti isomerism, what you are going to see is the position of the H and the OH. Okay. So here if you see now the H and the OH, they are on the same side of the carbon atom. So such a compound where we will be having a carbon nitrogen double bond, the two different groups on the carbon, and the hydrogen and OH group, they are on the same side. This we will be calling it as syn-aldoxide. So this is now syn-benzyl doxide. Okay, and if the H and the OH, they are going to be opposite to each other, then we will be calling this as the anti compound. I hope this is clear. Now the next also we have ketoxines to be exhibiting a geometrical isomerism. So how are we going to remember this? Now instead of the hydrogen, the ketoxines, this will be having another alkyl group. Okay. Now if it is going to have an alkyl group, obviously we will not be having a hydrogen, and we are not going to see a relationship between hydrogen and OH. And I've just now told you that if we have a H and OH on the same side, it is a syn. If they are opposite side, it is anti. But in ketoxines, you will not be having such a case. They are going to be alkyl groups on both sides of the carbon. So how are we going to name the ketoxines? Now let us see this. So if you see this structure, we have a carbon double bonded to nitrogen. Now nitrogen is having its lone pair and its OH. On the carbon you have two alkyl groups. Now what is this alkyl group? This group. First of all, you should know the name of this. I have taught this while we were discussing the nomenclature of the organic compounds. In case you are not well acquainted with the nomenclature of the aromatic compounds, so you can watch my lectures. They are all detailed lectures on the nomenclature. Okay, so we have this as benzene. Benzene has a formula C6H6. I remove one hydrogen from here. What is this group? C6H5, which we call as the phenyl group. Fine. Now on the phenyl group, I have put a methyl group. Now what is this called? This is called as toluene. Fine. Now from this toluene, if I remove a hydrogen, this is called as a toluene group. Okay. Now the structure says that this is a para-toluene. First of all, you can see over here on it is a PCH3C6H4. So first of all, this is C6H4CH3. You can understand. Now it says it's para. Where I have removed the hydrogen, this means this is 1 and 2 position. So this is going to be ortho. So for a para, what you will have to do is you will have to remove the hydrogen from here. So you are getting the whole spatial arrangement of the atoms. Fine. I hope this is clear. So this is a para-toluene group. Now, to tell whether it is going to be a syn compound or an anti compound, what you can see is that in this structure we have the OH group positioned over here. Fine. Now, what you will have to do is that you have to see that which is the group opposite it and which is the group next to it. So in reference to the para-toluene group, the OH group is present opposite to it. Alright. So we will be calling this as anti-para-toluene phenyl ketoxide. The one you are writing first, you will be mentioning that it is anti or syn to the OH group. Similarly, if I write phenyl group first, phenyl group and the OH, they are on the same side of the carbon-carbon double bond. So you will be calling this as a syn-phenyl para-toluene ketoxide. And if I reverse the positions now, what you can see is that I've reversed the position of the OH group. Now the OH group, this is on the same side as the para-toluene group. So if I want to write the para-toluene group first, what will I be writing? Syn-para-toluene phenyl ketoxide. And if I want to write the phenyl group first, I will be writing it as anti-phenyl para-toluene ketoxide. Okay, I hope this is clear. Whatever group you are writing first, just mention its relationship with the OH as syn or anti, and then write the other group, and that is going to be your ketoxide. Syn-Anti isomerism. Now, the azobenzenes, they contain carbon-carbon nitrogen, nitrogen-nitrogen double bond, and they also show geometrical isomerism. So here what you are going to have is two nitrogen atoms, both of them, they have lone pair of electrons, right? So the lone pair of electrons, and they're going to be two alkyl groups, phenyl groups. And what you can see is now these two phenyl groups, they are uh, on the same side of the nitrogen-nitrogen double bond. So this is azobenzene when we have two phenyl groups attached to the nitrogens bonded to each other by a double bond. This is azobenzene structure. All right. So we can say now that these two, they are on the same side of the nitrogen-nitrogen double bond. So this is a syn-azobenzene, and when they are opposite to each other, this is going to be a anti-azobenzene. Okay. I hope this is clear. So we have azobenzenes where we have nitrogen-nitrogen double bond showing geometrical isomerism, and we have the aldoximes and the ketoximes showing geometrical isomerism. Apart from carbon-carbon double bond structures, the alkenes showing geometrical isomerism, right? So that would be all for this lecture. I hope you have understood everything with the help of the models that we made for you. And now in the next lecture, we are going to continue the discussion further on geometrical isomerism. We are going to see geometrical isomerism in cyclic compounds. That is going to be very important and again, very interesting as well. So see you again. Have a nice day. God bless you.